I thought, so this presentation for me really came about because I really wanted to learn how unordered containers worked. And I'd heard that unordered containers are based on hash array map trees, which is like quite a mouthful. So I'm like, okay, where's the intro to hash array map trees? So I found this, someone that I've met, Mike Moskowski. I think he works at Cloudflare, and he's a blog called PopCount, which is a fantastic name for a blog, by the way. But his like intro is quite straightforward. Like that's it. That's all of it. And I'm like, this isn't really enough detail for me to like actually understand what's going on. I'm going to go look at the unordered container source code. So I go there, 2,000 lines, and like it's got all kinds of like fun stuff in there. Like, let me see if I can find you something. Nope, still going. Anyway, I think maybe, yeah, like that. This is like some mad unboxed tuples voodoo. And Johan Tibble loves performance, so he's basically like lovingly optimized like this to within an inch of its life. And like again, this isn't good enough either. So I'm like, okay, well I'm basically stuck. And then I found out that unordered containers is actually Ed Yang is the person who wrote the first version of it, and he has this like much simpler version. And that's like a bit nicer. So I was like, okay, so I stared at this for a while, like tried to implement it on my own, and I think I have like a much better understanding of what they are now. So I'm gonna try to demonstrate. So this is a Haskell notebook. Here are a bunch of imports. I'll explain all of them as they come up. I have this this fun binary new type. So this binary new type is exactly the same as like whatever it's wrapping, except it has a different show instance, so that I can show a number as a binary. Let me show you what I mean. So if I'm showing you the number like 55 as a, yep, but if I, so that's pretty handy. I'm going to be using this quite a bit when I just go through binary, and there's some bit twiddling involved in this, so I'm just going to pretend that, yeah. So we have a hash, which is just a 32-bit word, and we have a hashable class, which just turns anything into a hash. And I'm just going to go ahead and implement hashing for strings by taking the fnv1 hash, which is a fast hash function, just for convenience. So should have done that. And we're dealing with bitmaps. Bitmap, in this case, I've chosen 16-bit words, and because I've chosen 16-bit words, and 2 to the power of 4 is 16, I've chosen the number 4 here. If I'd chosen 8-bit words, this would be 3. If I'd chosen 32-bit words, this would be 5. So it's a bitmap, and there's a bits per subkey magic constant that's 4. And I'm going to be like doing these. I'm going to be using these operations on vectors. So just inserting something into a vector and growing it, or updating something into a vector. And these are persistent vectors in the sense that I'm not going to be destructively updating anything. So there's that. So we have, so now we come to the hash array map tree. So a hash array map tree is either an empty hash array map tree. Does it actually do anything when I, doesn't really do anything. Oh, okay, anyway, never mind. Or a leaf. So a leaf has a hash, a key, and a value. Why does it have both a hash and a key instead of just a hash? You could get by with just a hash with this representation, but if you wanted to support collisions, which are a thing that does happen, it's useful to have both the hash and the key, so you can add an extra constructor to have a list of collisions. So it's just makes things easier. I don't really think there's anything to be gained by like forgetting about the key. So the final case is a hash array map tree with many values. So it has a bitmap, which we defined above, and a vector of sub hash array map trees. So one invariant that we need to maintain is that the bitmap, the number of bits set in the bitmap, is equal to the number of elements in the vector. And I'll get more into that as we go on. So we have an empty hash array map tree, which is just a none. And I'm going to go. So this is enough for us to begin implementing insert. So I'm going to implement an insert which takes a hash, a key, a value, and returns another. So insert on is quite straightforward. all you have to do is return a leaf. That seems reasonable, right? So inserting on a leaf is also relatively straightforward. So, either the hash is equal to the leaf hash, which means you don't have to like do anything. We just need to update the value that's already at the leaf. So we do leaf hash key value. Oops. Okay. There we go. Or the hash is not equal to the leaf. So in this case, we want to like recursively insert the into, we want to upgrade the leaf node that already exists into a many node. And insert into that. So this is pretty straightforward. Like I said, the number of items in the number of bits set in the bitmap is equal to the number of elements in the array. So the only question here is, where does some bitmap come from? So we need to set one bit in this in a bitmap, but which bit? So to answer that question, let me start with an example. So let's see. So we do that. So what does leaf look like? So that's the hash of the string 1. So we had our bits per subkey before. So if I go, so that's that. So again, but if I show you that as a, so that's what it is. If we take that -1, we get a mask. So just the last 4 bits that are set. And we can take that and we can AND that with our hash. Okay. Right. So is this right?
You forgot the parentheses around the -1.
Ah, thanks. There we go, much better. Thanks. So we take that, and this can be reinterpreted as a number. So if I okay, so let me just set this bit. Okay, so that's the bit. That's what the bitmap should look like. So we're gonna write a function called bitmask that takes a hash and gives me back a bitmap. So let's do that again, just to make sure that okay, seems to work. So subbitmap is the bitmask of the leaf hash, because it's the leaf that we're upgrading to a many node.
Isn't H still hard-coded there?
Good call. So, okay, so we've done leaves.
This is for no collision.
Yeah, yeah. Sorry, I should probably point that out again. With this this demonstration, I'm going to assume that I'm just going to ignore the possibility of collisions. You could handle the possibility of collisions by having an extra, something like that, where you have like. You could have that, so that's how you could handle collisions. But I don't think actually so you could just like mechanically go through after I've like gone through everything and add an extra case to handle collisions. I don't think adding them is useful pedagogically, so I've just ignored them. But if you want to actually use this in production, like definitely you need to handle collisions. So we've handled leaves. So if I wanted to insert where my mask is my mask and my bitmap don't conflict. So basically, my mask again is the same bitmask function from before. Is like the value of the same bitmask function from before. But if it doesn't like coincide with my bitmap, since there's only one bit set, if that one bit doesn't exist in my bitmap already, that means there's space for it, and I can kind of grow my bitmap and grow my vector values accordingly. So what I can do is I can go. So I just OR my mask with my bitmap. And then what does my insert add function do? Insert add. Is everyone following so far? Have I completely lost everyone? Okay.
I think some of us came late. I know I did.
Okay.
So I'm sorry, but where did mask come from and why do you have it?
Oh yeah, mask comes a bit. Oh sorry. Good catch.
Okay, thank you.
Yeah, I was getting to that. But the other question is, where does index come from? So what is the index at which we insert at? So so I have to write a mask index function. Which takes a hash and a mask takes a bitmap and a bitmap and returns an index, which is an integer. So for example, like suppose I wanted to insert the value the string 10 and the so let me see. And the and the value 2. So that's h prime. So the bitmask h prime is that. So then what I want to do is I want to take that, I want to subtract 1 from it, and then I want to take the bitmap corresponding to like h, because that's the leaf that I have here, and I want to OR them. I want to AND them. So if I do that, right. Is that right? I don't think so. Sorry, I should have. There we go. So yeah, so that's right, and I want to take the pop count of this. So basically, what this is saying is since I'm using the new value as a mask, none of the other values, none of the other bits in the bitmap that are masked off by this have been set. So the correct index for it is 0. If like for whatever reason there were, the mask was like 1 or 2 or 3, that would be the correct index at which to set. So I'm basically this is saying that I need to insert it at the beginning, as opposed to some other value. So I can write that in my mask index function pretty easily. Okay, so that should work. And otherwise, I want to, so otherwise they do coincide, so I need to like recursively insert into the subtree. So the subtree is the element at the index is so this is almost right, which is why I have all these underscores. The thing that I've ignored so far, because it hasn't been super important, but becomes very important over here, is that if I'm recursively inserting, I don't want to kind of take a chunk of don't want to select off the last 4 bits of the hash each time. I want to move up the hash. So I need to have a shift parameter. So which is why I have like the shift that I defined here, and need to essentially increment it by, need to add bits per subkey each time. So I'm going to go ahead and do that. Does that make sense to everyone? Are people following why I need a shift?
I was freaking out because we didn't have it, and I was like really panicked.
Yeah, you're like, what are you doing?
How is
Okay.
any of this work?
Yeah, yeah.
If I take the same mask that we find,
Yep.
what's the need? So I'm looking forward.
Okay. Cool. So go ahead and okay. Okay, so just going to go ahead and move this up here. It's all in one place. And then we can actually go ahead and define from list. So actually no, I'm going to go ahead and define insert first, which is so takes a list of keys and values, and so from list Okay, so I can actually, so if I've, so you know, it's entirely possible I've done something horribly wrong, but and we'll see in a minute. But if not, okay, seems to have worked. I have imported a fun pretty print function. So that seems to be doing the right thing, actually. I've done this before, so yeah, seems right. So this is essentially what it looks like. Got a top-level menu node. It's got these 2 bits set, and which means it has 2 children. One of the children is another menu node. Again, 2 bits set, and leaves. So this works. Let's implement lookup, which is much, much easier. So I'm going to go ahead and implement lookup, which takes, again, a shift, hash, key, and a hash array map tree of key value, and returns. So lookup of. So this is essentially, this follows the structure of insert, but and it's much simpler. So hash key value of none is just nothing. Sorry? Should I have a, oh sorry, I do have a value. Thanks, good catch.
It's a little higher up on the screen, so.
Okay, like that? Actually, let me see if I can insert a cell below. Is that better? Yes, no? I can insert more cells below this. Better? Yeah, okay. Don't need a value. Sorry. Yeah. Which order did I take my mask index? Yep. Mask.
You want to talk us through what you're doing at the
Sure. So, like I said, I'm just following the structure of insert. So if I'm looking up something in an empty hash array map tree, there's nothing there, so it'll always be nothing. If I'm looking up something in a leaf, if the hashes match, it's just the leaf value. Yeah, I keep forgetting that selecting on my screen doesn't actually do anything here. So yeah, if the hashes match, it's just the leaf value. Otherwise, it's nothing. And if I'm looking it up in a many node, if the ANDing of them is 0, that means that there's an empty slot where there shouldn't be an empty slot, so it should just be nothing. There's nothing. There's nothing to return. Otherwise, I'm going to like look in the subtree and recursively look up from the subtree by shifting the hash, like increasing the shift as I do so.
Sorry, can you walk us through how you got shift?
Um,
I don't get about that.
okay, so the way that, so essentially the idea is that if I have this, if I have like a hash like this, if I'm looking, if I am inserting things at the first level, then I only need the first 4 bits of the hash. But if I'm inserting things at the second level, presumably I've already used up the first 4 bits of the hash. So I need to use the next 4 bits of the hash. So that's what the shift determines which 4 bits of the hash I'm looking at.
Every time you insert, you're going to increase.
Every time I recurse, I'm going to,
Oh, I see. Okay.
does that explain things? Yep. Okay. Yes.
When you insert things, do you have to know how far down in the tree they're going?
When you insert them, yes. Like that's what the shift does. Like you like increase the shift each time. Does, like I'm not sure if I understand the question.
So like you have to understand what's already in the tree before you can put something else in it?
Yes. I mean, yeah.
You start with a shift of 0 at the top of the tree, and each time you jump down a node, you shift increments as you want. And it's right there in the lookup code, right?
What happens if the tree is wider than the path?
I'm sorry. So then that's the case in which you have a collision, right? And I've like explicitly said that I'm ignoring that case. Like,
Like you're saying the shift increases every time you go down a level.
yeah. So the maximum number of levels that you can have is the like 8 in this case. Right? And if you're saying, hey, what if I like have run out of information but there's already something there, then that means you've hit a collision. So an early version of unordered containers said that, hey, because because unordered containers as of this writing also uses 32-bit hashes, and they say, hey, actually since we use like a fixed hash, all of your lookups are constant, worst case constant time, which is technically true unless you account for collisions, in which case like all that just goes out the window, and they're like, no, never mind. So anyway, I'm just gonna let me see if I can finish writing this up. Shift hash key subtree. Okay, so let me see if I can. Oh. Is anyone here not seen Haskell before? Okay.
I've never seen your editor. Which editor are you
I'm using iHaskell.
Huh?
iHaskell.
iHaskell?
Yep, it's a Jupyter kernel backend for it's a Jupyter kernel backend that's using Haskell.
So not everyone knows what a Jupyter kernel is.
Right.
Really cool. So maybe
Sorry.
you wanna-
Yeah, maybe I should.
1 minute and
Yes, I will digress. So the Jupyter kernel project is so it's basically it started off as a fancy REPL for Python, and it became really popular in scientific computing and like data science circles. And then they decided, hey, it's such a good idea. Why don't we add support for other languages? Like, why do we have it? Why can't it be like language agnostics? They added like an R kernel, and they added. I feel like they added at least one other one. I think they added some Scala stuff. So
it's a notebook.
Julia, exactly.
It's in your web browser and it's editable and it runs fast.
Yeah. So that's why they called it Jupyter. So it's Jupyter. So it's Julia, Python, and R. So Ju, Py, and R. And somebody else was like, hey, why can't we get this to run Haskell? So he put a lot of work into making it work.
Do you have like GHC running in the background? Because last time I tried GHC log.
Essentially, I mean, so that's what the kernel is. It's like essentially uses the GHC API to like run the code that I'm.
Where is the code running? Is it running in the cloud?
This is running on my laptop.
No, I mean the GHC is your GHC.
Yeah. But I mean, you can run this in the browser. There's this project called mybinder.org. Let me see. Let me see if I can. So this is like a service that other people provide that allows you to essentially run Jupyter notebooks in the cloud. And with a little fiddling, you can make Haskell work with it as well. So, my new Haskell notebook. This is in the cloud, and I can go.
Does this work decently well when you've tried it on larger projects?
I help maintain this library, so yes, it works really well for me. All right, well, it's starting. We'll get there. Yeah, I mean, I have I've put a lot of work into figuring out how to make this work for me. So, and given that I can edit the source code, whenever I feel like it, yeah, it works just great. Damn it. Maybe live iHaskell demo was not the best idea. Oh no. Okay. Let me see. Well, let's try again. Save page. Yeah, it definitely did work the last time I tried this. Okay, never mind. We'll come back to it later. So anyway, so let's look up. Oh, I haven't defined lookup. So that's correct. So this is enough of an API to actually use this for something interesting. So this laptop's kind of old, kind of slow, and running Fibonacci on it can be quite annoying. I'll show you. Of 1 is also 1. So I can of 30, say. Yeah, so that took a non-trivial amount of time. Fortunately, we have memoization. So this isn't the most efficient way of implementing Fibonacci. So if I wanted to implement it using the library that I just, the hash array map trees that I just made, I can do fib of so actually call this fast fib. Takes an int and it returns a tuple of int and okay. Yeah, the other thing I need is an instance of so this is like evil. Don't ever do this in production. But for the purposes of this demo, perfectly reasonable. This isn't 0. This is 1. Table prime. So essentially, I'm just doing the simplest memoization possible. In the case of 0 and 1, pre-computed. If for any other number, first I check if it exists, and actually no, I should. It's not quite right. So I need to return the table as well. But if it doesn't exist, I populate the table with sorry. One table is fast fib of n minus 1 and table, and then I2 is fast fib.
Scroll down more again.
Sorry. Oh yeah. Is that better? Okay. Table prime in I1 plus I2. Insert. Okay, so let's try that again. Are there any obvious mistakes people can see in my function? Sorry? Sorry? No. I mean, I've tried it on this example and it doesn't. Oh no.
Not with the identity function for a hash.
Sorry?
There can't be any collisions because you have.
Yeah, it's not an issue. Whoop. There you have it. Cool. So yeah, so I think this is fun. I think you can actually like make this work reasonably well by handling collisions. If you look at but the real value of this is not just that you can now implement hash array map trees yourself, but more so that you can actually go ahead and read Johann Tibble's implementation now. So if you kind of like go ahead and look at this, essentially this is not too this is not too impenetrable. So you have a bitmap indexing, which is our many. You have the leaf. You have the full, which is like an optimization for the case where every single bit is set, and you have the collisions, like I said. So I think like he's implemented his own array library, which is where a lot of the complexity here comes from, and a bunch of the fancier stuff, like just literally every drop of performance has been wrung out of this thing. But the guts of it are essentially the same. I guess hopefully this gives you a better idea of like what's actually going on when you use unordered containers. And hash array map trees are not just useful in Haskell; they're useful in they're the backbone of I think the Clojure collections library, which is where they came to Haskell in the first place. And if you want to make these faster, you could also like use the unsafe array functions instead of the safe ones that I have here. Do your own optimizations or whatever. And if you're interested in kind of like going through this, at your own pace, I've written a blog post. I also implemented deletion in the blog post, but I haven't here because it's not fun. It doesn't help me do a cute demo. Yeah, that's yes.
The HAMTs, that gets like maybe on the meetup page or somewhere a link to that.
Sorry, what do you want me to put there?
Well,
A link to my.
You're trying something called HAMT from scratch.
Yep.
Just a pointer to link to where to find that.
Yeah, sure. I can do that. So yeah, that's it. I'm done. Questions? Anything you want me to go over again?
Have you looked into hashes that deal with Haskell data?
Were you the one who asked the similar question last month?
Yeah, but since then I read that actually the hash interface in Haskell briefly was changed to use SIP hashes, and the salts were random, and then they had to yank it. They couldn't get it to work.
So if you look at so it's funny.
Sullivan retracted all of that.
It worked. It works just fine, but it broke every single user of the library because it made everyone have to care about it always.
Right.
Yeah. So if
it back because there was a riot, because we were all like, you broke our code.
so if you
On the face of it.
So the crashes were not in that library; they were in other people's code. We talk about seg faults or something.
That might have been separate. Never mind.
also the performance is so Johann Tibble actually like if you look at his like description of his hashable library, what he does for his hashing is actually not too different from what I've done here, even though it's like not a good idea because it's so from his point of view, it's more useful to have fast hashes that are like reliable than it is to have hashes that are like tamper-proof or like impossible to, or like just attack resistant.
But you need attack-resistant hashes. You don't need attack.
Yeah, and then you can always like swap out the, you can always, well, you can always define your own hashable instance.
Purpose library, then it's used by somebody.
Doesn't that ruin the probabilistic balancing though?
What does?
When you just have that as your hash, you don't actually have a random distribution.
No, but
Balanced, you don't have.
yeah, but even though you lose the probabilistic balancing, the data ends up much closer to like the other data in memory, which is usually what you want. So it's better for access patterns. Yeah, this is a debate that like you could have with Johan. Like I didn't I didn't come up with unordered containers. I just this is just what I've read. This is what in the course of learning about this.
What would the attack be other than making your computer slow?
Sorry.
Yeah.
What would the attack be other than making
Well, for this one, they don't handle collisions.
Well, yeah, but if you handle collisions,
Right.
everything in one bucket. It goes from log n to linear, or worse. Quadratic.
Okay. Yeah, that could be doing things that we need still. Which is a key reward.
Have you looked at all at C tries?
I have not.
Those look interesting, but I haven't yet.
Well, if you figure out how to implement them, let me know. Maybe we can.
There's a Haskell package for C tries.
Right. No. But I mean, if you can implement them from scratch, so please let me know. I'd love to know.
All right, so one of the things I remember about the Clojure library and all the talks about it and sort of the Bagwell HAMTs is that I think this is some of the questions you're getting at is there were a lot of sort of really good properties they had, and some of it had to do with how they use processors, fan out and everything. And maybe I missed that in the first part of your talk, but right, you've sort of given us the bare bones, but what's supposed to, there's some reason that these things are supposed to be like really good outside
Oh,
of
yeah.
optimization
It's because
that has to do with how they use hash lines or something. Like,
yeah.
can
So
you speak a bit about that?
sure. So the central thing to understand about these, in my opinion, is the way that the bitmap interacts with the number of elements that the number of elements in the vector. So an easy way to implement these would to just allocate like a vector of 16 elements each time you had a level. But that means that you waste all that space when there's nothing to put in the arrays. So the central like innovation here, in my opinion, was the idea of like having a bitmap, which doesn't take up a lot of space, to determine like to tell you everything you need to know about how many elements are in the array and how to access those elements. So which means that if there's nothing in the array, then you don't have to allocate anything. And if there's the 16 elements, you allocate 16 elements. And that's I think that's the specific thing about them is that they manage to achieve really good memory usage, as well as just having these being really easy to update. More?
Can you explain why the instance hashable int is a bad line to put production?
Yeah, well, we were talking about it earlier. So usually there's, so I wasn't completely accurate. So I think this is like not too different from what the actual hashable library in Haskell does. But when you're designing a hash function, you want it to be like, some people want it to be random. So it's sort of like bucket, like to put data to spread data like really well across like a bunch of different buckets. And this doesn't do that. So if you have like 2 and 3, they'll be like pretty close to each other, and like, when sometimes for a hash map you want them to be as far apart as possible.
The more important part from that was when you import an HAMT library, you don't necessarily want to import a hash instance for integers for everything.
Yeah, you don't necessarily want this one. You want to be able to like choose it, but yeah, I think actually, so the difference between this and what Hashable does is that Hashable at least takes a salt, so you can choose the salt that you use when you're hashing things. So you're not stuck with like one will always hash to 1.
But I think the hashable for integers just XORs the salt of the integer.
Yeah, maybe.
So it
I don't know.
doesn't do anything especially random. Last time I tried it looked like that.
Yep.
So do you think it would make sense with this to like factor the whole thing into like
Oh, that's interesting. That's like, that sounds like what, like, that sounds like Jasper's thing from last month. What do you mean exactly? Like, so the first, so you have a, so you like somehow merge both the map and the hash map representations into like this one unified thing?
Well, you would have something kind of like an int map, and
Mm-hmm.
then you would just have a hash map that's a map from ints to bytes.
Interesting. I'll have to think about that some more. It's pretty cool. Sorry, is that something that exists already? What's it called?
Byte string try.
Oh, cool. I've heard of that. I didn't realize that's hard work. Cool. Yeah. Yeah. I guess that's it. That's all I have for you.